putting it up on DCourse site, probably within a day or so, and it will be due. It's going to be very simple, so we'll have it due back in a week. Maybe 10 days, but let's just say we'll have it back. It should be very simple. It's just to get you to exercise some of the things you're learning. No curveballs at all. It's going to be very, very straightforward. Nuclear engineers will be volunteers. There will be two questions that you have to answer on the policy side as well, so it's not going to be simply text. Okay, today we're going to talk about reactions and neutrons. Now,
Will that be turned in lecture?
That's a good question. Nowadays, it seems popular to scan these things in. What would you like?
I'm ambivalent. Either I can grade
Right.
either way.
He's ambidextrous, so he can take it in his left hand or right hand. Well, okay. Let's just say either, and I suppose that's true for Mansook as well. If you got the homeworks back as a PDF or a hard copy, do you have a preference? Austin?
I don't have preference.
If it's a PDF, then in Adobe Acrobat, they can actually use the yellow balloons to actually comment and so forth. So, okay, let's make it easy on everyone. Send it in as a PDF. Good. Okay. Let me ask now, this is the semester that 101 is being taught, correct? Okay. Where are you in 101 right now?
Quantum mechanics.
Okay, so you haven't gotten yet to, so I'm going to be telling you some things about reactions today, which some of you may know from your undergraduate studies, but some may be new to some people. I mean, nothing here is going to be terribly profound. Okay, so it could be that I'm a little bit ahead of where Professor Bernstein is right now. Okay, but don't worry, it's all going to be fun. Okay, just a quick review of what we learned last time in terms of fission. The basic picture is that a neutron, fast or slow, will come through the nucleus. Some nuclei under the irradiation of thermal neutrons, very slow neutrons, will lead to a very high probability of fission. The nucleus, which we argued could be modeled as a liquid drop, will begin to form, and then the enormous Coulomb repulsion, this very highly charged droplet, will drive the two fragments apart. There's a scission. There'll be some prompt neutrons given out, and some prompt gamma rays, and then the daughter nuclei will accelerate down the Coulomb hill, the Coulomb potential, picking up enormous amounts of energy, total kinetic energy of about 160 MeV. Then there'll be subsequent gamma de-excitation, very fast, 10 to the minus 18, 10 to the minus 15 seconds. And then after that, there's our energy budget, all totaling about 200 MeV, 2 to 3 neutrons, prompt and gamma rays, and fission product gamma rays, totaling about 14 MeV on average. And then after these, you get these fission products, they're unstable. So very rapidly, you will actually begin to beta decay, changing neutrons into protons as this thing skis down the potential down to the bottom of the valley of the chart of the isotopes there. Okay, and then by the way, this just shows you why you get 200 MeV. Very important idea we want to reinforce. The average binding per nucleon is less for a single large nucleus of mass 236 or 240 than it is as two separate pieces, mass 90 and mass 140. We also mentioned, for reasons that you will learn in your 101, and if you take 201, which I usually teach, and they teach again, in a little more detail, the nucleus, when it fissions, overwhelmingly comes out as an asymmetric mass fragments. Now, we've drawn two specific nuclei there. but the combinatorial ways that is in the hundreds, if not thousands, of different isotopes that one can get in terms of the primary fragments. These are called the primary fragments, but of course, after they land in Valley stability, as I say, they end up having to beta decay very rapidly and then more and more slowly down to the Valley stability. Okay, the two things that matter in this course, by which people make weapons or make reactors, is plutonium-235. The minority component of green, 0.7%. Four main ways of making it. Today, the tool of choice overwhelmingly for even countries which are not first-tier technology countries is sort of gaseous, the centrifuge. And we will have Scott Kemp here, who's a visiting professor from MIT, who's an expert on this. He's written a lot on the whole threat posed by the proliferation of centrifuge technology. He's going to give a guest lecture here on March the 9th. Other methods, gaseous diffusion, electromagnetic separation, but in fact, I think all countries with a minimum of technological capability these days use the centrifuge. Plutonium is something that is made, is cooked up during the reaction, during the operation of a reactor, and when the fuel rods are taken out, the fuel rods are laden with plutonium, and they can be dissolved and melt through various chemical engineering processes to separate out the plutonium, of which is 239 is the one that is useful in making nuclear weapons. A detail we'll get into later, if you overcook, if you actually are running a reactor for nefarious purposes, you don't do as you do in a power reactor, like let the thing operate for 6 months, take out the fuel rods, put a new neutron, which is a typical cadence for a power reactor. What do you do if you're using a reactor clandestinely to make plutonium for weapons?
Every few days.
Yeah, sort of a couple of weeks. And in fact, that's one of the signatures that of ill intent is when you see a power reactor, or even it can be a research reactor, even tens of megawatts, like a university might have, being operated 2 weeks on, a week off, 2 weeks on, a week off. The reason is that if you let the fuel accumulate in there too long, you make a lot of plutonium-240, which emits neutrons spontaneously. It's a spontaneous fission spontaneously, and that will give pre-detonation when you compress the fuel and kind of done the weapon. So you actually, if you want a very high ratio of 239 to 240, you have to lightly cook the fuel, take it out, put it back in, so forth. You can't overcook the fuel.
Professor, is production or is fission of plutonium-239 also a concern?
No, not the spontaneous fission, but that's for slow neutron radiation.
Leaving the 239 in there for too long.
Yeah, that's the point. Yeah, that's the issue. Okay, so let's talk about reactions. Here is a prime example of this was in fact patented by the British in 1946. It was recognized that if you take the two heavy isotopes of hydrogen, deuterium plus tritium, one can make a reaction which is extremely exothermic, very energetic. You make a helium-4 plus a neutron, and I think, well, you can calculate this now. Now you have the toolkit. Where do you go to calculate? Suppose I said take out a half piece of paper where would you go? What resource would you need to calculate that Q value? I'll give you a hint. You can use your computer. Yes. How many people have rummaged around the chart? Good. The NNDC, National Nuclear Data Center, you can go to the IAEA, they have a similar one there, and you can go find, what do you go look for on the NNDC chart? Symbol, capital Greek delta. Yes, equivalent to mass excess. Yeah, so it's basically the mass excess of D, mass excess of T, minus mass excess of alpha, minus mass excess of neutron, gives you that 17.6, which, when you look at it, is a quite stunning number. Here you've actually got 5 nucleons at play. That's 3.5 MeV per AMU. What is that number for fission? How much energy out? How many nucleons? Yeah, slightly less than 0.8 something. Okay, so this beats the stuffing out of fission. This is why this looked like the dream. You know, the dream of as people said, with the electricity too cheap to meter energy out of seawater. That's only a half truth. The deuterium you can get out of seawater relatively easily. Tritium one has to make. And once you get this reaction going, of course, the fusion reactor can make the tritium that you could then harvest and then reinsert back into the system. Okay. In general, nuclear reactions, let's talk about two-body reactions. They can be more complicated. You have what's called a charged particle reaction. Deuterium and tritium, hydrogen 2 and hydrogen 3, have +1 charge each. So you've got two charged particles merging to give you A plus B, C plus D. Something of great interest in this course, of course, are neutron-induced reactions. We talked about neutron-induced fission, which I didn't put down here, but that's a reaction. This is what's called a neutron capture gamma reaction. A neutron will bombard a nucleus, be a thermal neutron, be captured, and form the same nucleus with the same Z, the same atomic number, and then emit a gamma, because when you drift in a neutron, you're now in an excited state, and that energy has to be shed, and so it takes. High energy photons themselves can induce reactions. In fact, they can actually break up light nuclei. So an energetic, a few MeV gamma ray impinging on a deuteron can break it up into a proton and a neutron with kinetic energy. That's called photodisintegration. Very commonly, in fact, normally the dominant cross-section in any two-body channel is elastic scatter. That is almost never a small thing. And that's where you have for example, proton plus carbon going to proton plus carbon with, in the center of mass, the same energy. So you have not excited the carbon, you've not taken energy out of the system, they've simply scattered in the center of mass or center of momentum frame. You would have the proton coming in. Velocity larger, suggestively. And then they go out at some angle with the same velocities that they came in. And then this is theta. Okay, we talked about a famous case, which was the Rutherford scattering, Rutherford's law, by which he determined that it was eminently clear that all the positive charge in an atom was located in a very, very, very tiny, almost point-like object, because he was able to predict this 1 over sine to the 4th theta over 2 law, due to, again, the Coulomb scattering. Then you have inelastic scattering. I can shoot in a high energy particle. That proton can go out or whatever, a neutron, an alpha particle, whatever, but the target nucleus is bumped up to an excited state. And then, of course, because you've taken energy to promote the nucleus to an excited state, whatever the secondary particle coming out is coming out with lower kinetic energy, of course, because energy is conserved. Anything is possible, but there's a few rules. You have to conserve energy, you have to conserve charge, and you have to conserve nuclei number. Okay. That's kind of obvious. Okay, now here's an interesting question for you. This was a stunning thing. I could have actually made a previous bullet, which was Lord Rutherford's claim that no one would ever get profitably use nuclear physics to extract energy. Back, I think he made that comment in 1933. Said anyone who's talking about practical uses of nuclear technology, specifically for energy, was talking moonshine. 1938, discovery of fission. Literally less than 3 years later, we had the world's first reactor, the graphite pile, built under the Alonzo Stagg football stadium at the University of Chicago. There was a zero power reactor, but he actually demonstrated neutron multiplication. It was a critical reactor. Within 3 years of that, less than 3 years, we had first deployable nuclear weapons. We had electricity on the grid in 1951. And 3 years later, we had the Naval Nuclear Propulsion Program. We actually had, reactors at sea, very robust reactors that were able to power submarines going underwater, continuously for months at a time, like that. And my comment is, it was like falling off a log. Can't miss. Can't go wrong. It was just child's play to get energy out productively from fission. Even though, as you just calculated, the energy per nucleon involved in the process is slightly less than 1 MeV. By the way, that's a big number. Anyway, here we have, the fusion reaction just talked about. Here, seems migrated. Deuterium plus tritium goes to an alpha particle very tightly bound. Because it's very tightly bound, has a very low mass excess plus a neutron, which means you're going to get a huge Q value. There is the Thomson-Blackman patent. People wanted to get in early, like today's sort of tech entrepreneurs. They saw a profit in this, so they patented the fusion reaction. President Eisenhower in 1955. I actually have the document there, Project Sherwood, announced by executive order, that he designated a certain number of laboratories, of which Livermore was one, to actually do the engineering. At that time, it was viewed as just taking an engineering detail to make a fusion reactor, plasma fusion reactor, work. And there was one university in there, quite interestingly, and you'd never guess, it was NYU. Because of the role, they played a small but important role in the Manhattan Project. Anyway, I have that founding document, and I think it was originally classified and then declassified, but they said, a year or two from now, energy too cheap to meter. Well, where are we today? Maybe, just maybe, we will have demonstration of break even with the ITER facility in Cadarache, France, which is a fusion reactor by a 6-party fusion reactor. The European Union, there's Russia, China, India, US, and Japan, I think, in there. It will have cost $60 billion. It's the size of Evans Hall. Maybe we'll have break-even. My friend, some of you know at MIT, Dennis White, former chair, actually has this brilliant idea called Spark, and they've started a company called Commonwealth Fusion Systems in Massachusetts, which is going to use high-temperature superconducting magnets, very high field, 20 Tesla, like 200 kilogauss magnets, to make fusion reactor much more compact. They claim that they'll get a gain of 140 megawatts thermal in 5 years. If that's true, that would be as revolutionary as the discovery of the transistor. It's an astonishing thing, and if they work. And if you want an exciting job, they're hiring. They've got more money than they know what to deal with. They've already raised $150 million in capital to do the magnet work. They're only allowing a certain number of companies who've already invested to go to the next phase to give them $500 million. But $500 million, they claim they're going to do the job in 5 years. But anyway, when all is said and done, forget about whether sooner or later it will have been a century, if ever, that we get fusion. So, what's the difference? The Coulomb barrier. You looked at my notes. The Coulomb barrier. The Coulomb barrier. The Coulomb barrier. Here's the problem. Neutrons have no charge, and even a zero-energy neutron can just drift into the nucleus and be captured. In fact, I'll actually show you in a little while that for many nuclei, slower neutrons actually have a vastly, orders of magnitude higher probability of being captured and causing a reaction. Charged particles, you have to have a certain minimum kinetic energy before there is an appreciable reaction rate. If you're below the Coulomb barrier, then the probability that there'll be a reaction will be much smaller or even negligibly smaller. So let me actually motivate this. We talked about it a little bit when, and we'll go over this again, when we talked about Rutherford's famous experiment. Here's the deal. So let me look at this in a very semi-classical way. Here is, I'm going to draw a potential energy diagram. There's total potential energy as a function of the separation between two objects. This will be a carbon nucleus or some nucleus here. We'll nail it down. Let's not worry about recoil effects. And another nucleus, for example, it might be let's do aluminum, and an alpha particle coming in like this, which is heating for 2 protons, 2 neutrons. This is 13 protons, 14 neutrons, like that. So, what have we learned about the nuclear force? Qualitative. What's the one thing you got to know about the nuclear force? Short range, exactly. You really don't. They really don't know one another is there until they're basically touching. Okay, so the thing is, you want to get to a situation where you have like that. Okay, that's when you have actually an appreciable nuclear force. So the nuclear force pretty much traces the nuclear potential pretty much traces that shape you saw for the shape of the nucleus itself. So in fact, it's kind of a square well. with kind of a rounded shoulder. And just to approximate this, it's perfectly fine to say that the range of the nuclear force for two nuclei, when you start getting appreciable reactions, is to say that when the projectile and the target are touching, this is not a bad approximation for a first cut at what the Coulomb barrier is going to be. Now, we know what that is. It's approximately 1.4 Fermis times the sum of a to the 1/3, a of the projectile to the 1/3 plus a of the target to the 1/3, like that. In this case, I chose the limit of 27 because that's easy. A cube root of 27 is 3. You pass. Okay, so it's 3. In the case of 4, 1.5, 1.5, 1.5, okay, let's call it 5. Yeah, maybe 1.7. Okay, this is 4.2. This is about 2.2. That's about 6.4 Fermis. Outside of that, you really don't feel the strong force. Inside of that, it could be absorbed or scatter or do something else like that. Now, what is the law? So this is what the nuclear component of the force looks like. It's short range, and the potential is relatively flat. What does the Coulombic part look like as a potential? What's the general behavior of the law?
1r².
That's the force. What's the potential?
Oh, 1r.
Yeah. Okay. So there's a repulsive potential here. Outside of this thing, it's kind of going down like 1/r. Inside, or at a point like entering a homogeneous thing, it actually doesn't diverge. It actually will kind of go over like that, but that doesn't matter like that. That's what the Coulombic potential looks like. The sum of the two, and I don't have colored chalk here, outside it's the purely Coulombic force. All of a sudden, it will go down the sum of these two. I'll actually just make a very heavy line here. That's the total potential. And you see, it has a barrier. Okay, like that. Now I'm going to. So then you ask the question, if you say that the force outside that touching radius is negligible, the Coulomb barrier is just the potential, Coulomb potential at this sort of kissing radius where the two nuclei classically just touch. And in our nuclear units, it's Z1 or Z projectile, Z target, E squared over R, which is, in this case, 13 times 2 times, this has been in your little workbook each time, MeV Fermis, is how we express E squared, divided by 6.4, and I'll spare you the math. This turns out to be a little less than 6 MeV, 5.9 MeV. Now, I've neglected the recoil effects and all that, but you can see nuclei which are lighter than aluminum will readily, in Rutherford's famous experiments, head-on collisions between the alpha will actually touch and be absorbed by the target, which is why he saw the deviations from the sort of the classically predicted 1/sine to the fourth behavior. How to think about this? I find it a silly pursuit, but some people like playing miniature golf. How many? You play miniature golf? Okay. There's a typical hole there that's very difficult. It's called the volcano. It's a you hit the thing and they actually slope the hole up like a small volcano when there's a hole in the top. And that's exactly what's going on. That's simply a gravitational 1/r potential. We drew the picture before about Rutherford's famous experiment. Things at a large classical impact parameter would follow a hyperbolic trajectory like that. Things closer in, things like this, would then make a very sharp thing. And then, of course, dead on, if you were running Coulomb barrier, the thing could actually be absorbed. And that's why his famous law, like this, if it was a truly point-like object, at some point for light nuclei, you started seeing deviations because we're getting nuclear absorption. It was perfectly Coulombic here, and this is these point of the deviations which told him what was the size of that nucleus. Anyway, that's an analogy. Think about, the volcano in golf. Now, you might say, gee, one proton. What's with that? It's like a few hundred kilovolt Coulombic energy. It turns out, though, that is a very large energy for, if I make a plasma, even though plasmas are very hot, the average energy of those ions is very low, and they're only getting maybe some tens of Fermis away from one another. There is some magic that happens in real, honestly, but this quantum mechanics treatment of scattering, which actually allows reactions to happen even at very low energy. Not you. Who's going to answer? What's it called? Tunneling. In quantum mechanics, you can have a phenomenon having a classical potential barrier, which is higher than the energy, but there is a very small probability that the particle quantum mechanically will leak through the barrier. And so even though sometimes particles can be very far, the Coulomb barrier does not allow them to get very close, there'll still be a very small probability that you will get a reaction. In the case of the neutron, remark it, and the neutron just goes in, you get a reaction. And that's why fission goes like gangbusters, and fusion is very hard. Okay, so yes. This is a general notation we use. Here's the Chadwick's famous reaction for the discovery of the neutron, like this. You can write this, that's a perfectly good way of writing it. That's how you wrote your chemistry in high school. But in nuclear physics, we use a little bit of a shorthand, which is this notation here, which is target, residual, and then a parenthesis, beam and ejectant. Now, some reactions are a little more complicated. You can say, well, who's the ejectant, who's the beam? But anyway, you normally write the reactions like in this way, like that. Okay. Let me go for about another 5 minutes here. So here's the question: how do you determine what the cross section is? If I take, for example, neutrons at 1 MeV, right, take a thermal neutron, you'll find that that nuclei are all over the map for reasons that for no apparently good reasons. You will find the absorption cross section for one nucleus might be hundreds or thousands of times greater than another. But anyway, the question is, how do you determine those numbers in the first place from an experimental point of view? Let me erase this. So imagine that I have a bale of hay, and I've kind of randomly put marbles in the bale of hay. And I can even tell you how many are in there. But there's no fair kind of poking around with your fingers and taking a look. But what I will give you is a shotgun. The question is, how with a shotgun can you tell the average size of the marble? Well, it's kind of obvious. I'm sure you've done this at home. Live in a rural area, you've probably done things like this. So what you do is you do a nuclear physics experiment. You actually shoot particles up through the bale of hay. And what you'll find is you count how many pellets went in the front side, how many pellets went out the rear side, and there'll be a certain decrement. If it's really negligible density of hay, then in fact the hay itself will play no role. The only ones that will not make it out downstream in the same collimated beams you came in with are the ones that will have been, in this case, undergone an elastic collision and taken out of the beam. So that's what we're going to do. And so the definition of this is a cross section, and I'll just wrap up here shortly and leave the rest of the time for Professor Knopf. The basic thing here is that if I actually are able to do what's called an attenuation experiment, right, I know how many are coming in, how many are going out, then the number that are scattered, which is the difference between the two, is going to be the incident number times the number per cubic centimeter times the thickness in centimeters, and then a cross section which we're going to derive, which is described in terms of an area, effective area, which is in centimeters squared. So if I measure the number that are scattered and I divide that by the number that go in, and then take out the thing having to do with the target that I have prepared, which you know about, that leads to cross section. Now, this is easy to do. And if you're going to do it, it will actually give you problems to exercise on this. But there's one thing you need to do. So I said, suppose I gave you a slab of aluminum. Went down to the shop and I gave you a sheet of aluminum, which is 1/8 of an inch thick. How many aluminum nuclei are there per cubic centimeter? You know how to do that. Haley knows. Yes. Now, if you go to Google or something, the density you find is typically in what units? Yes, which is not quite the same thing, but we know how to get there. And by the way, just let's see if you have a good feel for numbers. What's the density of water? How much is water weight per cubic centimeter? What, by definition? Aluminum is fairly light. What's the density of aluminum? Wrong. That's what your iron is 7.9. Aluminum is 2.7. Sand, concrete, things like that typically might be 2. What's the density of lead? 11. What's the heaviest? Yeah, that's a weird fish. It's that's a 19. I think uranium and plutonium tend to be like 18 something. But the heaviest are like 20 grams, close to 20 grams per cubic centimeter. That's a lot. That means 25 cubic centimeters you've got a pound. Okay. Let's just do some numbers. By the way, so if I say that the density of aluminum is 2.7 grams per cubic centimeter, how do I know what's the number of atomic nuclei per cubic centimeter? You're a chemical engineer, so you know this. What do I do now? Yes, and the molar mass to 1 part in 1,000 or so. This makes it really easy for you. Is A. Now, up until about a year ago, a couple of years ago, our old friend carbon-12, the goal was defined to be the number of atoms in 12 grams of carbon. Now they've defined the mole some other way like that, which are never wrong by more than 1 part or a couple of parts per thousand. If you just simply take A. For iron is 55.9 something rather than 56, but as I say, you'll never go wrong when you can just use A. Now, this is really easy because in the case of aluminum, A is 27. So the number density, which is per cubic, just pure number per cubic centimeter, is going to be, in this case, 7, is 1/10 times the mole. Okay, so in this case, it's 6×10⁻²² per cubic centimeter. And away you go. Okay, let me stop here. Again, this comes from the war years, maybe a little bit earlier. It turns out 10⁻24 centimeters squared is a convenient benchmark for nuclear cross sections, and therefore somebody mischievously called it a barn, as in as big as a barn door. With that, listen. Questions? No.
Okay, well, I'm returning now to some of the highlights in the Kaplan book. I don't know if you plowed through all of it. He writes beautifully, but there's a lot of material in there. And there's no particular reason why you should figure out what's more important versus what's less important. So my job today is to summarize a couple of the key points that are really worth remembering. And I was just reflecting on the fact that I was starting with this grand basic study in 1950, and 1950 is 70 years ago. It's staggering. But what's important to know is that most of the core concepts of nuclear strategy were developed in that 20-year period, 1950 to 1970. Now we'll see, with new technologies coming along, technology can force new concepts upon us, but these are really centrally important ideas. And I'll say a few words about I didn't know these people in the 1950s, but I got to know them later. So I have a few remarks about some of their bringing to life. So again, after the war ended and the bombs were dropped, Donald Douglas, who was the head of Douglas Aviation, the main aircraft manufacturer in the United States, proposed that there should be a separate group of civilian strategists who should work for the Air Force and then maybe the Pentagon more generally on nuclear strategy. And that became the RAND Corporation, which stands for Research and Development, purposefully benign, anodyne name, so it couldn't really convey what they were really doing. It was highly classified work. Even the existence of RAND was not known for quite a few years later. They built a building in Santa Monica, right on the border, Southern California. And that's where RAND started. Today, RAND has the same building, although it's been greatly modified and expanded, and also a big facility in Pentagon City, you know, the shopping center across the street from the Pentagon in Washington DC, in Northern Virginia. And they also have a few other scattered sites. They have a Pittsburgh office, they have a Belgium office that do domestic analysis, totally unrelated to military issues. But in the beginning, this was all military and it was all nuclear weapons. They attracted a variety of interesting characters. You can imagine why would someone go out to such a place that was so new and not clear what they would do and how they would do it. And one of the startling personalities of the early years was the great Albert Wohlstetter. Wohlstetter became a world famous figure in the field. One anecdote, he was a PhD student in philosophy at Columbia, and he quit the program because he informed his advisor that his advisor did not know enough about philosophy to educate him. And this was a kind of hallmark of Wohlstetter's personality. He was a very self-confident, almost authoritarian figure, but he did some amazing work. And he was the lead investigator on something called the RAND basic study, or the selection and use of strategic air bases. And their basic homework assignment was to determine, given that the US had, and this is in the pre-missile age, we just had long-range bombers. If the bombers were based on the coasts of the United States, in order to get off the ground quickly and head toward, head toward the target, which would be in the Soviet Union. Was there any problem with that? And capital discussion, a lot of detail, which I won't go over now. We did a bunch of gaming studies and other studies and concluded that actually placing the bombers on the coasts was the single worst place to place them, because they were most vulnerable to attack. And the core problem that they articulated was the vulnerability of retaliatory forces. Vulnerability of retaliatory forces is the key hallmark of the stability of deterrence. If you're going to hit me, but you know that you can't disarm me, and therefore I can return the favor, then you're going to be deterred, presumably, from attacking. But if you have high confidence that you can destroy not me, but my retaliatory capability, then you have an incentive to strike first. And that's not good for me. Okay? So Iran, by this time, the Soviets were developing intercontinental range ballistic missiles, which could attack the bomber bases. And Wohlstetter recommended, he gave a briefing about 40 times, 40 times, all over the government, to sack and to get rid of the Air Force Base in Nebraska, in the Pentagon, to key civilian people in the Congress. And he recommended that the bases be relocated inland into the Dakotas, Missouri, and other inland sites, making it more difficult for the Soviets to attack and disarm the United States. And again, this highlighted the notion that US retaliatory vulnerability is a core characteristic of US strategy. Some of the other key people involved in the study were a man named Harry Rowan, who later became the president of the RAND Corporation. And you wouldn't be aware of this, but there was another famous figure. Unless you have studied anything about the Vietnam War, you probably not. So during the height of the Vietnam War, there was leaked a major classified study called the Pentagon Papers, which was an analysis of how the US developed its decision-making in Vietnam. And the key leaker was a man named Daniel Ellsberg, who was an economist trained at Harvard. But he was at RAND, and he became associated with Wohlstetter a little bit later than this period. He's younger than Wolstead by quite a bit. He's still alive, Ellsberg, and he lives in Kensington, up the hill. I used to live in Kensington, we were neighbors. He's now in his 80s and he's written some major books on his role as a nuclear planner and so forth. Rowan was fired as president of RAND because Ellsberg was at RAND and used the RAND Xerox machine to copy Pentagon papers and release it to the New York Times. So there was some interesting personality connections here. All this work done on the RAND basic study was highly classified, not known outside of a small circle of military and political figures for years, through the 50s. But the US started to change its basic policy based on this study. And then in 1959, Wolstetter received approval to write an unclassified article, which came out not with the details, but with the core ideas. And that is published here in January 1959 in the article in Journal of Foreign Affairs, Albert Wolstetter, Delicate Balance of Terror. And the key theme here was that it was not the case that if you have a lot of nuclear weapons, and I have a lot of nuclear weapons, it's a stable, determined situation. Wolstetter it's only stable, again, if the retaliatory capability is invulnerable to attack, and that has to keep being adjusted because of new technology. More accurate systems, you get submarines launching ballistic missiles off the coast, very short warning time, this can all change it. So Wolstetter claimed that the balance of terror between the two sides, which was US-Soviet, was very, very delicate. And he coined that term in 1959. I cite his my own comment that he was a significant figure for 40 years in US nuclear strategy. One of the other key figures we read about, we discussed earlier, Bernard Brodie, had also been at RAND at this time. He originally was a big supporter of Wolstetter, and then he became convinced that the delicate balance of terror concept was just being used to support funding for more and more nuclear weapons and more delivery vehicles, and Brodie became very opposed to the concept. And he and Wolstetter developed a hugely gargantuan animosity between them. It was of enormous magnitude. And I mean, hatred doesn't begin to capture their relationship. I later had a small role in this, which I'll relate to in just a minute. I was a cameo performer in this Greek tragedy. While this was being circulated and briefed and the bases were being changed, there was a separate effort, totally unrelated, which during the 50s was the Eisenhower years. And the Pentagon initiated a committee called the Gaither Committee. A man named H. Rowan Gaither, he was an attorney, very plugged into Wall Street, chairman of the Ford Foundation. He was plugged into sort of high society and knew a lot of the top Eisenhower political appointees. And he chaired a committee to review itself U.S. nuclear strategy, totally separate from the basic stuff. And what the committee basically produced was the fact that they projected the growth of Soviet versus US missiles in the 50s and 60s, and claimed that unless there was a 50% increase in DoD funding and a major investment in civil defense programs, that the US population would be highly vulnerable to a Soviet nuclear attack. This was actually an idea based on limited intelligence information. It was before we had really high precision satellites. So part of this was guesswork about what the Soviets were doing. Soviet Union was such a secretive society. But it was actually picked up ironically in the 1960 presidential campaign. Eisenhower completed 2 terms as president, 52 to 56, and 56 to 60. In 1960, his vice president, Richard Nixon, ran on the Republican ticket, and the Democrat was John F. Kennedy, senator from Massachusetts. And Kennedy ran on the critical view that under Eisenhower, they had developed a missile gap, which was putting the United States in great jeopardy of an attack by the Soviet Union on the United States. This turned out to be erroneous. Kennedy did not know it was erroneous at the time of the 1960 campaign, but in 61, McNamara went out as Secretary of Defense and reviewed all the intelligence and determined it was not correct. This has estimates of different programs, how many missiles the U.S. would have. The Navy was getting into the missile business of the SSBN, the surface ballistic nuclear submarine business. So there were estimates of how many missiles we would build versus how many they would build. And again, this was more a comparison of missiles. It wasn't a dynamic analysis like Wolfstead had done on the vulnerability of retaliatory capability. It was a quantification, judgment about numbers of missiles. But because also one of the themes of the Gaither report was the need for a massive civil defense program, this was picked up by the intelligence community, and the Gaither report gave legitimization to civil defense. 2 of the key intellectuals of the time were Herman Kahn and Edward Teller. Very different in nature. Kahn was originally from Bayonne, New Jersey. He went out to the West Coast. He studied physics at UCLA. He got a summer job at Rand, and he never went back and never completed his PhD. He stayed at Rand. And he became a major proponent of thinking about nuclear war. He wrote a major tome called On Thermonuclear War, which listed about 14 different scenarios for fighting in nuclear war. And some people thought this was very innovative, but some thought he was nuts. Have any of you heard of the film Dr. Strangelove? Is that ring a bell with any of you? So Kahn was the model for Dr. Strangelove, the kind of mad scientist who just enjoyed thinking about mass murder using nuclear weapons. But he himself said, in order to protect the population, we need a vast, complex, very expensive civil defense program. On a technical level, was Edward Teller, the father of the thermonuclear weapon, a critic of Oppenheimer during the 50s. And Teller also, and of course he was the founder of the idea of the Lawrence Livermore National Lab as a competitor to Los Alamos National Lab. And Teller also became a major proponent of civil defense. You have 2 gigantic figures like this supporting a public policy program, it's going to get funding. And in my own days, in the 50s and to the 60s, I mean, I was a kid climbing under a desk and thinking about what tunnel to go through to protect myself against a nuclear blast, which of course would be possible, but in fact. But that's what kids did at that time. And it's partly because of the tremendous articulation of the need for it by Kahn and Teller and the Gaither Committee. Any questions about this so far? We're not, notice we haven't had a major civil defense program in the last 50 years. We got a lot of weapons pointed at us right today, right this afternoon, 10 to 3 Pacific time. This place could be wiped out in about 30 minutes or less. Now, again, what we see are different intellectual strands, sometimes in parallel with each other and sometimes interconnected with each other. Another key figure was was this man, William Kaufman. Kaufman came from an upper crust family on the Upper East Side of New York. He came from a wealthy family. He went to private schools. He went to Princeton and Yale. He got his PhD in political science from Yale. But he got interested in nuclear strategy as well, and he went after the Rand Corporation. And he had written a very seminal piece on the requirements for deterrence as a Princeton discussion paper in the 1950s, which was highly circulated. His main theme was that the way to have stability in a nuclear arms competition is to focus on counter-force weapons. Focus on weapons that can destroy the weapons of the adversary. And if both sides had such capability, that would be a stable situation. Not counter-value weapons or counter-city weapons that were just designed to kill millions of people. At the same time as this, there was like an intellectual fight about counter-force versus counter-value at Rand. There's a totally separate fight about defense budgets for nuclear weapons between the Air Force and the Navy. The Air Force had been in charge. They had SAC. They had General LeMay, a huge, larger-than-life figure, who was a bully and a tough character and all that. And he said, my aim is to kill as many of the Russians as possible, as quickly as possible. I can't kill them fast enough, that's what he said. I want to kill them faster than they even realize they're going to be killed. Because they became kind of counterpart of the Soviet Union. You don't know that. At the same time, though, the Air Force was developing higher accuracy weapon systems, ICBMs, and of course the bombers, the gravity bombs, could be dropped with some precision. Totally separately and in a competitive fashion was the Navy. Admiral Rickover was the father of the nuclear Navy for nuclear submarines, and some of his associates were all involved in pushing for submarine launched ballistic missiles, SLBMs, that could be carried on the SSBMs. But those weapons were very high yield, low accuracy. So when Kaufman began to advocate the counterforce, he sort of inadvertently was arguing in support of Air Force weapons and not Navy weapons. And the Navy has lots of friends in Capitol Hill, and they pushed back very hard. So there's a huge fight between the services over these weapons. And there was Daniel Ellsberg, one of the other players at this time, and Andy Marshall. Andy Marshall was a friend of Wolstedter's, and later on, some years later, a younger man, just 1 second, named James Schlesinger, who was a Harvard-trained economist. He had gone to Rand, and he had written a book when he was at the University of Virginia about defense budgets, which caught people's eyes. So later on, when Nixon became president, Schlesinger was appointed as head of the CIA and then later as Secretary of Defense. And I got to know some of these people right around that time in the 70s. And Marshall was at Rand, and he had a wine cellar. He was a wine connoisseur. And he said that he was going to leave his wine collection with his friend, Jim Digby. Digby was shown earlier. There. Here. Digby was he was involved in the basic study, even though his name was not on the report. Digby was also sort of a lackey of Wolstedter's. Marshall left his wine cellar with Digby, saying, this is 1973, I'm going to join Secretary of Defense Schlesinger. I should be back in 6 months. That was 1973. You know when Andy Marshall retired from the Pentagon? 2 years ago, 2018, at the age of about 96. He organized something called the Office of Net Assessment, which became a major think tank within the Pentagon. Think about the long-term threats of the United States. And he just recently passed away. Andy Marshall passed away. I think he was almost 100 years of age. He was a man of very few words. I was once in a briefing with Schlesinger and Marshall, where Marshall said absolutely not a single word. He didn't even utter a sound. There was no sound of any kind emanating from him or any part of his body. These men devoted their lives to the subject. Another key figure at the time after Kennedy became elected was McNamara. McNamara was a Berkeley undergrad and a Harvard Business School MBA. Then went into the private sector, started at the Ford Motor Company and rose amazingly through the ranks and became the youngest CEO of the Ford Motor Company and the first non-family member to be the head of the Ford Motor Company. He was hyper smart, very workaholic. So he had a great affinity for numbers and analysis, and he loved all this stuff. So he became Secretary of Defense under Kennedy. He soaked up this stuff and was a real expert, which is not true of most secretaries of defense. I'm sorry, I didn't get back to you. Yes, sir.
No problem. I was wondering why was the Navy's weapons were low accuracy, higher yields? Was that just kind of a time limitation?
Yes, right, just figuring out how to get the SLBMs and the SSBMs to get them to fly. It was a big enough job. It took a long time to figure out how to deploy high accuracy, lower yield SLBMs. Yes, sir.
At the time that we're moving from counter value to counter force strategies, do we know what the Soviet nuclear doctrine was? As in, if we left their cities alone, would they have actually left ours alone?
Yeah, I think the answer is probably no. We were guesstimating. We did have increased reconnaissance satellites. We had some civilian intelligence at high levels, only some of which has ever been declassified. But the Soviets had excellent intelligence of us, and plus we talk all the time to each other. Whereas the Russians are fantastic at, I told you, keeping secrets and stealing secrets. They're the best in the world at both. We're probably the worst in the world at both. We don't keep them and we don't steal them. Steal them pretty well, but we don't keep them very well. McNamara became enamored of Kaufman. And this was way before Schlesinger. Schlesinger was in the 70s. McNamara was 1961. And he recruited Kaufman away to be like his personal advisor on nuclear strategy. And then McNamara became convinced that this was such a dangerous time, the public needed to be better informed about what was going on. And they established the publication of something called the Secretary of Defense Posture Review. What's going on in the Defense Department? What are the key programs? In all fields, not just nuclear. And Kaufman was put in charge by McNamara of overseeing the writing of the first posture review. This was in 1961 or 62. And Kaufman held that post while being a professor at MIT from 1962 to 1980. Every Secretary of Defense felt it was essential to think through these issues and to articulate carefully what U.S. strategy was. Kaufman was a man of few words, smoked a pipe. Did you see him at MIT, Carl? No. Okay. He was a professor at MIT in political science, and they gave calculations by exchange calculations, how you calculate damage by each side in case of a nuclear exchange and so forth. He lived on what's the drive right by Memorial Drive. He lived on in a high-rise Memorial Drive. He's married with no children. He was married to this job. This is what he did. He passed away about maybe 10 or 15 had a dry sense of humor. Another feature of Kaufman's analysis was, we're not only concerned about the preservation of the United States, we also are concerned about our allies. After all, NATO is a collective defense treaty. We are there to protect the French and the British and the other members of NATO. And therefore, we have another feature of our strategy called extended deterrence. We are extending the deterrent to our allies. And that also meant that counter force weapons were much more credible capability than counter value weapons, which was different from what the French themselves thought of. One of the great figures of French nuclear strategy was General Pierre Gallois. He was an amazing Volstetter-like figure in France. I had the opportunity in the late 70s to visit him. I was a young kid, not knowing much about almost everything. And he said he couldn't meet me at his office, but he could invite me to dinner at his home. I'll describe this briefly. He went to his home, a beautiful, huge apartment on the right bank, 16th arrondissement, which is like Pacific Heights. It's the wealthiest part of Paris. I was there alone. I came in, met him. He said, we will have dinner, Madame Gallois, myself, and you. The three of us. I thought it would be a big crowd, just the three of us. A gigantically long table. General Gallois was at one end, Madame Gallois was at the other end, and I was in the middle. And had various servants, a whole flock of servants who served the dinner. And I don't know what we ate, but the food was off the charts. It was fantastic. And we had some discussion, and then he basically said, now, General Gallois, clearly he controlled every facet of what was going on. So now we will sojourn to my study to discuss the issues. And he looked at his wife and he went like this. But she was dismissed. He dismissed her. Not a word was said. She got up and left. I never saw her again. I went into the study with General Gallois, and his English was pretty good, much better than my French. And we had some brandy or something, and he said to me, he said, you may want to know what's behind our nuclear weapons. He said, I will tell you. He said, we French have fought many wars since 1870. We have fought the Germans in 1870. We fought the Germans in 1914. We fought the Germans in 1940. Later on, we fought the Algerians. And in between the Algerians and the Germans, we fought the Vietnamese. We have lost every war. Every war. This is why we must have nuclear weapons. It's the only way to defend the fatherland. I was having some sort of coronary thrombosis during all this, but I managed to survive it. So, you see, a lot of it depends on your historical perspective, your feeling of your country and where it came from and all the rest. Or as Kaufman said, that's all very interesting, but it's not relevant to today's world where the Soviets can wipe us out. You need counter-force weapons, not counter-value weapons. Here's what again I repeated. Kaufman was the chief author of this posture from 61 to 80. In the later years, when Carter was president, former Lawrence Livermore led director, Harold Brown was the Secretary of Defense. The hyper-smart physicist, Columbia educated, bachelor's, master's, PhD in physics. I think got his PhD from Columbia at the age of 21. And then he went out to Lawrence Livermore Lab and rose quickly up through the ranks to become the director of the lab. And later he was president of Caltech, and then became Secretary of Defense under Carter. But ironically, after Carter was defeated in 1980, he kind of disappeared from public view. He got into finance. He was at Lehman Brothers. He didn't stay a major public figure And he passed away just a few years ago in his early 90s. The total master of all this material, but not as publicly well known as some of these other people. This is McNamara. This is McNamara, a briefing on the Vietnam War in well, he's up there above paragraph. Kaufman's skeptical of the utility of civil defense programs. Here's a con, more about a con that I mentioned. On thermonuclear war. Dr. Strangelove film. This is Peter Sellers, the actor who played Dr. Strangelove in the film. If you haven't seen it, it's a fantastic film. You can draw your own conclusions of its meaning. And a major figure. I remember as a boy, my father bought me a 4-volume set called The World of Mathematics. Does that ring a bell with you? A lot of kids our type would get that. And the editor was just very famous mathematics papers from ancient times right up to the current period of the 60s. And the editor of all that was just very familiar with mathematics, but he was a writer. He wasn't a mathematician. His name was James R. Newman. And so that I'm losing my pointer here.
It's the battery's going out.
Oh,
I have spare.
okay.
Yes, yes. Yeah, I'll send it to you.
So Newman wrote a review of Kahn's book on thermonuclear wars, this thick. It's got all the different scenarios for nuclear exchange. And this is a quote, this is in the Kaplan book. Newman's quote of a review of our thermonuclear war. And Newman wrote about Kahn's book. This is a moral tract on mass murder, how to plan it, how to commit it, how to get away with it, and how to justify it. That's in the Kaplan book. So this is a not very positive review of Kahn's on thermonuclear war. I also mentioned on this slide the references on the bottom page 248 of the Kaplan book. Those are some of the best articles on nuclear strategy of the time. The references on the footnote on page 248. Do you have?
You want to?
Okay, okay. I'm sorry, was that all clear? It was a little disconnected. Did you catch that? Any questions about what I'm referring to? Okay, another feature of the evolution of nuclear strategy had to do with the development of nuclear war plans, which were called Single Integrated Operational Plans, or the SIOP. SIOP. We know that the Soviets had something comparable. And basically, these are different, it's like a cookbook saying, if you want to attack these targets, this is the mix of weapons that you can use best to destroy them. If you want to attack this target, this is the mix of weapons. If you only have this mix of weapons, these are the targets you can attack. Okay? It's not as though, oh my God, we're in a nuclear crisis. How do we figure out what to do? Everything is pre-planned. Hundreds of plans to use for nuclear weapons. And this is during the Cuban Missile Crisis. This is the XCOM, the executive committee that Kennedy convened to try to get out of the Cuban Missile Crisis without a war. That's JFK right over there. That's McNamara. This is Paul Nitze. George Bundy was the National Security Advisor. I don't see him. He must be. I'm not sure who he is. This is Dean Rusk, Secretary of State. This is George Ball, who became a big critic of Vietnam policy. Oh, this is Bundy over here. This is Cyrus Vance, who was the Deputy Secretary of State. We had a major crisis over Berlin. One of the main themes of US policy was how to protect Berlin from a Soviet grab. And Berlin was a divided city in a divided country. Germany was divided 2/3, West Germany 1/3, East Germany. Berlin, which was in East Germany, was itself divided into 3 parts, Western, US, French, British, and 1 part Soviet. I visited Germany when it was divided during the Cold War. Extremely scary situation. When you went from West Germany into East Germany, as soon as you went through the checkpoint, it's a very highly forested area, and through all the forest, you see tank turrets sticking out. The Soviets had hundreds of tanks in East Germany. There was always concern about the nuclear war with the Soviet Union will begin with a crisis over Berlin. There's a whole story of how we got out of these various crises, including 1961. So let me just say, oh, I'm sorry, it's 3:30. Oh, we're out of time. Let's see, what else do I have to do here? All right, I'll have to go over some of this the next time.